Okay. Consider this. I briefly overviewed what the fuzzy system is, and I believe I explained this kind of chart to transfer your vague or linguistic information into some mathematical form. And it is actually transforming a set. As you know, in many real-world problems, the design data, objective function, and constraint are not mathematically crisp. I want to use this one to explain or to contrast the fuzzy system. In real world, the crisp objective function, crisp constraint, and crisp data are very hard to achieve, and many things are just fuzzy or linguistic form. So that we are using the fuzzy system, and all these fuzzy systems are based on the fuzzy set theory. Okay. Okay. Let large X be a classical crisp set of objects. And let's call this universe. And whose generic elements are denoted by small x. It's a just simple basic set theory. We all know this. And there is another concept called membership. Membership in a classical subset A of X. In high school mathematics, we usually use this as a U. You know, U. And there is some set A or B, and we know what the union of the two sets is, and what the intersection of the two sets is, and what the complementary of the set is, right? Membership in a classical subset A of X can be viewed as a characteristic function mu sub A from X to this closed set, bounded set, 0 from 1, such that one or 0 if X is inside of A, if X is not inside of A. You know, membership is a characteristic function. So let's say this is our universe, and I'm here. then mu sub ax is, if I'm here, it's a 0 because I'm not the member of A. If I'm here, then this function will return 1 because I'm the member of subset A, right? It's a very simple function which maps from this maps from universe to this. Okay? That's the classical membership function in a set theory. And there is one thing to consider is, this is a universe overall set, and this is also a set of real numbers, and we call this set as a valuation set. It's just name. Okay. Set A is called a fuzzy set if valuation set is allowed to be the whole interval from 0 to 1. In a classical valuation set, you only use 0 or 1. Okay? So in the same sense, if the valuation set's value are totally used, every number between 0 and 1 are used, then we can call A is a fuzzy set. Okay? The fuzzy set A is characterized by the set of all pairs of points denoted as and this mu sub A, a function of x, and we call this a membership function. And this, as you know, this membership function are transforming the universe into an interval from 0 to 1. The minimum value of this interval membership function is 0, and the maximum value of this function is 1. Okay? The return value of mu sub A is always between 0 and 1. Okay. One example of a fuzzy set. Consider the classical example. If mu parenthesis x, if the x belongs to A, it is 1. If not, it was 0. But the fuzzy set, it's one example of fuzzy set A, is a collection of pairs. Okay? So for example, let's say fuzzy set of A of a comfortable temperature for human activity. Temperature for human activity. It's one example of a fuzzy set. So, I copied this from a textbook. So the temperature unit is Fahrenheit. So 62 Fahrenheit. That's a little bit cold. So it has 0.2 value. 64. Still cool, but much better than 62. 66.8. 68.95. 68, the perfect temperature for human activity. But 70, a little higher. 72. 74. 80, too hot. This is one example of fuzzy set. This is a set. Okay? Compared to the classical set, classical set only have the element. But in the fuzzy set, it has the pairs. And this inside of these pairs, you have the element and your membership function value. Okay, so in general, if large X is a finite set given as x1, x2, xn, the fuzzy set on X can be expressed as okay, notation is a little funny, but it's a mu sub A x1 vertical bar x1, which means when x is x1, the membership function value, and you all have to summarize it until it reaches the end. Okay. And if you write it in a summation form, it is nothing more than this. Okay? This is the generic form for fuzzy set if the X is finite set. We can count the number of elements one by one. But if you go further, if the set is not finite, such as a real number, set of real number, we cannot count, then that's the form. You can just transform your summation into the integrals. Okay? The reason why we are doing this is like this. Think there is a universe and we have a fuzzy set A, fuzzy set B, okay? First, and every point, for example, let's say this is x1, this is x2, x3, okay? In classical crisp set theory, mu sub A x1 is 1, mu sub A x2 is 1, mu sub A x3 is 0, right? Mu sub B x1 is 0, mu sub B x2 1, mu sub B x3 1. But think of this thing. In a fuzzy set, recall that we are now thinking of this kind of thing. Now, virtually think of some contour. You know, in a fuzzy set, there is no clear boundary. But think of some kind of contours. And the contour of A, contour of B, like that. Okay? So if you look this set from this side, well, you will have this kind of elevation, A and B. Okay? Let's assume this is fuzzy set, then mu sub A x1 is not 1, maybe it depends on the location, it could be a 0.8 or something, but it still have some value if you evaluate with respect to mu sub B, maybe 0.1 or something, right? Mu sub A x2, I don't know, maybe 0.5, mu sub B, mu sub B x2 is also 0.45 or something like that. That's the different story at all, right? It's a fuzzy set. Question? In this? Okay. And the next step is, the reason we are utilizing this set theory is we'd like to, it's because we'd like to utilize the set operation, union, intersection, and complement. Okay. Okay. Mu A union B is defined as mu A, mu B is also maximum of the two. Or if mu A is larger than mu B, if that's the definition. And A cap B, similar. It's an intersection of minimum of the two, or okay. Okay, so graphically, if this is some x, this is a membership function value, the maximum is always 1. So the summation of all the membership function at each point should be equal to 1. So let's say this is a mu sub A, this is mu sub B, mu sub A, mu sub B. Okay? Then the summation function value is this maximum of the two. Union. And intersection is here, blue one. Okay. Okay. Until now, we talked about the basic of fuzzy set theory, and let's look the fuzzy set optimization of this fuzzy system. Okay. Since in conventional crisp functions, if we are to optimize this crisp objective function with respect to the crisp constraint, the problem will look like this. Okay, that's for the crisp function. But optimization of the fuzzy system, since these objective and constraint functions are characterized by the fuzziness, so there is no crisp function to optimize or use as a constraint. Everything is explained in terms of membership function, mu's. So our objective function is also given as a mu. Our constraints are also given as mu. Okay? In fuzzy systems. Okay? Okay, let's write it. Since the objective function and constraints are characterized by the membership functions in a fuzzy system, in conventional optimization, we got to know what is the design variable. In this case, X. X represents the design. Okay? Design, or since these fuzzy systems are heavily used in control system or decision makings, or a decision can be viewed as the intersection of the fuzzy objective and constraint functions. Okay, this is a kind of a huge leap from this conventional optimization theory, so I will bring up some example. Let's say there is a huge crane like this, and this beam is I-beam, I guess. Okay, and we usually call this is the depth of girder. Okay, so this let's say in our example, the objective function is the depth of the crane girder, which is a variable x. Girder is not a function, but this depth of the girder is x. Should be substantially greater than 80 inches. That's one typical and most simple, one of the most simple fuzzy objective function. This is a very vague and linguistic form, and your optimization objective function is given like this. And you are supposed to then, what depth is the optimal based on this objective function? So, in fuzzy system, fuzziness comes in here, substantially greater than. What is substantially means? Very hard to transform into direct number, so you may have mu sub f. F means for the objective function. It is my design, and changing this vague and linguistic form into the fuzzy system, this process is called fuzzification. And there is not a single and unique solution of fuzzification. It's up to you. Okay? So, If x is less than 80 inches, I will give a 0 valuation, which is not good in fuzzy system, right? The objective function requires it should be substantially greater than 80. So, and how can I model our membership function based on these two? Well, I can model like this. X minus 80 minus 2. And if you plot this kind of membership function, it should be always a non-negative value. The value should be within 0 and 1, right? And it should capture your vague and linguistic information into mathematical form. X-axis is x, the depth of the gutter, given in unit of inches. This is membership function value. 1 is the maximum. This is 0, lowest. If you draw this graph, it will look like something like this. It will approach asymptotically to 1 as x is greater, become larger and larger. This point is 80. If it's less than 80, everything is 0. But if it's greater than or equal to 80, your membership function value will like that. Okay? It's my fuzzy design of objective function. Okay. And let's say there is one more constraint. Constraint is also fuzzy. I mean, information is vague. So let's assume the constraint is given like the depth of the gutter should be in the vicinity of 83 inches. This one says that, well, it should be around 83. How much around? I don't know. So, based on this kind of vague information, you can make your own fuzzy membership function. And this specific example, I'd like to use mu sub g because it's a constraint. It's my design. And if you plot that specific function, let's assume this is around 83. Then your constraint membership function is look like this. At 83, the value will return 1. Perfect. Okay? and the design or decision is described by the membership function mu sub d. It's a design membership function, and it is given as design can be viewed as the intersection of fuzzy objective and constraint functions. So it is intersection of this mu sub f, mu sub g. Okay? And this is 0. If you do the intersection operation, this is minimum of these two. Minimum of these two. So our mu sub d is intersection. Okay, what do you think the optimal solution then? The point with highest valuation. It can also heavily affected by your constraint and objective function as well. If your design of fuzzy constraint function is more narrow peaked, something like that, then your location of optimal solution will change. If your design of objective function is more like exponential design or something, then your location of optimal solution will also change. But anyway, based on current design of fuzzy system, the optimal solution will be the location where the highest valuation exists. That's the fuzzy system optimization. And two things to mention here. Transferring this linguistic information into the fuzzy system. This fuzzification process, it's a totally arbitrary. There is no rule, no mathematical proof or something. So, using this fuzzification, this process usually depends on the expert in crane design or domain knowledge design expert. Sometimes it requires a teamwork, gathering 3 or 5 crane design or girder design expert and discuss about, is this shape acceptable or not, or something like that. That kind of process is required. Also, fuzzification of this constraint, you need the discussion of the structural engineers and the like. Okay? The domain knowledge expert should use this fuzzy system, like us. The fuzzy system expert cannot do this one. Okay? Question? Mathematically, it's simple. The optimization problem of a fuzzy system is given like find large X which minimize okay, subject to comparing with the conventional optimization theory, this term is exactly the same. Minimize large X, which minimizes the objective function. Subject to, in conventional thing, this is constraint. Okay, but in fuzzy system, form is a little bit different. Each of these constraints should belong to large G sub j for many number of constraints. This G sub j are called as a fuzzy interval to which the function G sub j x should belong. You know, all this objective function and constraint should transform first into the fuzzy set or fuzzy membership function like this. Okay, so each constraint should belong to some here. So in our example, this G sub 1 is this colored area. Okay, and the thus the fuzzy feasible region S is nothing more than the intersection of all large G sub j. Okay, you can recognize this graph as your new Venn diagram in your fuzzy set. Is defined by the membership function mu sub S feasible region is nothing more than this intersection of the fuzzy set is defined as the minimum value of this fuzzy membership function out of everything. This is the mathematical definition of your feasible region, which in this example, this red area is your feasible region. Since a design vector large X is considered feasible when this is non-negative, the optimum design is characterized by the maximum value of the intersection of the objective function. And feasible region. That's what we did here. The intersection of this objective function and this feasible region is this blue area. Right? And the maximum of the intersection of feasible and objective function is the optimal design in fuzzy system. So, mathematically speaking, the maximum value where this design membership function is given as minimum of, which is in turn an intersection of objective function and once again all the intersection of all the constraints. Right here. Okay, during this explanation, I forgot to mention about this complementary, if you have a set A, complementary of set A is given like this. If this is your universe, this is your set A, complementary of the A is the rest of that, right? And in fuzzy system, it's nothing more than just 1 minus your membership function. Okay, question? I will draw a simple diagram to further explain the fuzzy systems. this not only the fuzzy optimization, but the fuzzy system itself are usually utilized in these 4 steps. Fuzzification, and there must be some fuzzy rule banks. And fuzzy inference, and the opposite of this fuzzification is called as defuzzification. Okay, input is crisp. Output is also crisp. And from the fuzzification, we define the fuzzification means we transfer this fuzzy system into our set of membership functions. So during that process, the output of this fuzzification, if we input something to the fuzzified system, is that truth value. And fuzzy rule banks, if you have lots of rule banks, from here to there, activated fuzzy rules are transferred to the fuzzy inference, and this inference engine, your fuzzy rule will inference, and the inferenced output is the clipped fuzzy membership functions. And from this defuzzification, this clipped fuzzy membership functions will be transformed into the crisp output. Okay, I guess this diagram at this stage doesn't make any sense to you, so I will explain one by one by an example. Okay, there was one research project was done, which is the forecast. In that specific project, the input was 2 tanker supply. You know what the tanker is? It's an oil carrier, crude oil carrier, tanker supply. So input was a tanker supply and tanker demand. You know, in a oil carrier market, we only have 2, demand and supply. And based on this, we'd like to forecast tanker new order tonnage. You know, if we can guess exactly how much new order of an oil carrier and how much tonnage is, then it will be greatly helpful to shipyard or broker or bankers and the like. So that was kind of a very simple system. Tanker supply we can get from some statistics, and tanker demand we can get this kind of information from ship owners association or oil carrier. I mean the company like a Hyundai Oil or something like that. Based on these two, we'd like to estimate this new tanker new order tonnage. So for short, let's say this is a TS, tanker supply. And let's say this is TD, tanker demand. And tanker new order tonnage, let's call it this new order tonnage. New order. Okay? And we have basic information, such as if the supply is low and the demand is high, then price or new order demand will be high. And we'd like to utilize this kind of information based on our own experiences. So in order to utilize this thing, you know, if the supply is high, demand is low, then we can say that the new order tonnage will be very low. This kind of rules or knowledge is very fuzzy. So we decided to use this model this system as a fuzzy system. And originally we noticed that from the bottom line, supply can be low, medium, and high. Demand also low, medium, and high, right? Very straightforward. So this is what we did originally. This is the truth value, 0.1, and this is the tanker supply. Okay? The union is million deadweight. So based on information, we make our membership functions like this. We define this. If the tanker supply is less than 203 million deadweight, then we definitely can tell this is low supply. Okay? Sorry, this is a straight line. And if this tanker supply is around this, we define this as normal, medium or normal supply. And if this region is a high, okay, for the input value, we did this. You know, as I mentioned before, this is fortification, but anyway, before continue, we have to define for everything. For TD, This is for TD, also in same unit. We define this is low. This is normal. And this is high. Okay, this is for tank demand, and let's throw it over here. Let's say this is new order demand, also in million deadweight. This case a little bit complex because so from here they call very low, and for this low, and for this medium, and for this high, for this very high. Okay, based on the background research, we constructed this kind of fuzzy system. And we have all this fuzzy or linguistic or vague information, such as if tanker supply is high and tanker demand is low, then tanker new order tonnage will be very low. Something like that. So, in a fuzzy rule, the rule is in the form: if x1 is a1 and x2 is a2, and then y is c. These are one fuzzy rule. Okay? So, based on this x, y, x1, x2, x3, xn, and y are fuzzy variables. In this case, our example, the fuzzy variables are three: TS, TD, and NORD. And we need the rules. So we made also very simple rules out of this simple system, which is this. You don't have to have this kind of matrix for general fuzzy rule, but in this system we only have 2 input fuzzy variable and 1 output fuzzy, so I think it's very nice. This direction is TS and this direction is TD. Here is low, TD is low, normal, and high. TS is here low, normal, high. So the rule was, if supply is low and demand is low, then based on our knowledge, the new order demand will be medium. And that is rule number 1. If the supply is normal and demand is low, then new order tonnage will be low. So, that was our fuzzy rule matrix or fuzzy rule banks. Okay, questions so far? Okay, I think everybody understood how we design this fuzzy system and how we design our fuzzy rule. And it's a very straightforward, right? There is, if the demand is very high and supply is very low, then new order demand will be very high. It is just straightforward. Everybody can tell that. But in this 4, 1, 2, 3, 4, it is kind of not to expect, not easy to expect if you don't have any background about this tanker market also. But anyway, making a fuzzy rule banks is straightforward, right? We don't have to construct any mathematical formula or something. We can just directly construct a rule based on our knowledge, domain knowledge. Okay? Okay, the next step is once this fuzzy system is defined, the next step is follow this thing. Crisp input. For example, we design this supply, demand, and new order demand like this. And crisp input. What would be if the TS is 240 million deadweight and demand is 168 million demand. How will be our new order demand? Okay, we have these 2 crisp input, right? So we have this crisp input. And based on this membership function in fuzzy system, we have to transform this crisp input to the fuzzy truth values. Okay? Things like that. This is 240. This is 168. Okay? Fuzzification means 240. So we have, because this is exactly 0.5, we have 0.5 of low in TS and 0.5 of medium, normal in TS. Okay? Here, for TD, I don't know exact number here, but we have some value of low, maybe 0.7 or something, low in TD, and 0.2 or 3 of normal in TD. So output of this fuzzification of this crisp input is fuzzy truth values. We have two crisp input. At the same time, for one, we have two fuzzy value. We have also two fuzzy value. So 4 different fuzzy value will be transformed into the fuzzy rule banks. Okay?